This is Module 14, Routing Concepts. This module, as well as Modules 15 and 16, are all about how routers operate and different types of routing options like static or dynamic routing. Much of this chapter was covered in CMCIS 151, but there's a lot of new material here as well. So as you should know, the main purpose of a router is to route packets. Traffic comes into the router determines where the packet is going and decides on the best possible path to get there, if it can get there. The router accomplishes this task by relying on the routing table. The routing table is a listing of all the networks the router is aware of. If the network is not in the routing table, the packet is dropped because the router does not know where to send it. So in this routing example right here, a user on the 192.168.1.0/24 network is trying to send something to the 192.168.3.0/24 network. So it sends its packet to its default gateway, which is R1. R1 de-encapsulates the packet, finds out the destination, again, 192.168.3.0, and does a lookup of its routing table to find out what's the best possible path. Well, in this situation, he's really only got two paths. He can send something out his Ethernet link here or something out his serial link. But he does a lookup and he finds out that 192.168.3.0 is actually out its serial interface, or he finds out he needs to send it to 192.168.2.2, which is on R2. So he sends this over to R2, and R2 will then have to do the same exact thing where it de-encapsulates this packet, figures out that, oh, it's trying to get to 192.168.3.0, and then has to do a lookup of its routing table to find the best possible route. And we can see it's the first one here, 192.168.3.0. It's directly connected, just send it out the fast Ethernet 00 interface. So it does, and it finally gets to its destination. When a router determines the best path, what it is doing is looking for the most specific entry in its routing table. Cisco calls this the longest match. It is possible there are multiple routes that could fit what the router is looking up. In this example here, the router is looking for 172.16.0.10. All three of route entries technically are good, but 172.16.0.0/26 represents the best entry because it's the most specific. Remember, a /26 network, there are 64 total hosts. And a /18, there's over 16,000. Well, we're only looking for number 10. So that fits within the /26. So this would be the best possible path. The same goes for IP version 6. We're looking for the most specific or the longest match. So here we're looking for a destination of 2001 DB8 C000, and then a bunch of zeros as indicated by the double colon 99. And so when we look up at our route entries, we find out that 1 is too big. Entry 3 doesn't even match because it's looking for a subnet of 55555, and ours is all zeros as indicated by the double colons. So entry 2 is the best path here because it's the longest, most specific match. Routers build the routing table by default the moment you activate any of their interfaces. The first thing it does is it takes all the directly connected networks and adds it to the routing table. The router doesn't have to do much of anything here. The router knows about these networks because it's physically or directly connected to the network. In this example, for instance, R1 is on the 10.0.1.0/24 network. In fact, it has an IP address of 10.0.1.1, as you can see from this topology. That immediately gets added to the routing table, as does the other two networks, 10.0.3.0 over here and 10.0.2.0 over here. R2 and even the ISP, they're going to do the same thing for its directly connected networks. After that, routers must learn about other networks that are not directly connected to them. We call these remote networks. From R1's perspective, it can't know about this network over here hanging off of R2. It can only learn that one of two ways. It can learn this statically. In other words, the network administrator manually tells the router how to get to that network, or it can learn about it dynamically. Dynamically means that R2 is telling R1 about the remote network. It is considered dynamic because if someone, for instance, administratively shuts down R2's gig 000, this network over here will no longer be accessible. So R2 will actually tell R1 about that, and R1 will no longer try to send traffic to that destination. In static routing, this doesn't work because R1 has no idea this network is accessible or not. It has a static route, and it's going to just push that traffic on through to R2, where it will be dropped because this network no longer exists because the interface is down. The last option here that they mention is the default route. A default route is a static route, but one that isn't specific to any network. It's essentially a catch-all, a last resort type of option. It's not possible, for instance, for R1 to know every network in the world. In fact, you don't want it to. The bigger your routing table is, the longer it takes to look anything up, which means your network traffic is going to be majorly delayed. R1 doesn't have a route to Google, for example. It doesn't need it. The default route should forward the traffic to R2, and R2 similarly doesn't know Google's address, but it has a default route too that points to the internet. So the traffic that started on R1 and we didn't know what to do with has made its way to the internet through the default route, where a router with more knowledge of Google's address will eventually handle it and forward it to the right destination. When traffic comes into the router, the first thing the router does is de-encapsulates the packet so that it can see the destination IP address in the header. Next, it does a lookup in the routing table for the network, picking out the best possible path. The router then re-encapsulates the packet and sends it out the destination interface. If the network doesn't exist in the routing table, the packet is dropped. It can either send something to a directly connected network, to a remote network, or drop the packet because it doesn't have a route to the destination. In this video, PC1 is going to send traffic to PC2. PCs, just like a router, have a routing table, but it's very minimal. In most cases, the routing table of a PC just says send it to the default gateway, which in this case is R1. So PC1 needs to send something to R1. It does a lookup in its own routing table. It says send it to 192.168.1.1, whose MAC address is 00-10, and PC1 will do exactly that, sends it off to R1. R1 gets it, de-encapsulates the packet, and finds out that it's trying to get to 192.168.4.10. It then does a lookup into the routing table, finds the network, and finds out to get there, we have to go to 192.168.2.2, which is R2's IP address, or just send it out gig 001, which is its exit interface. So it sends that out, re-encapsulating it, sending it out to R2. R2 gets it and has to do the same exact thing, de-encapsulates it, finds out the destination is 4.10, does a lookup in the routing table, finds out that it has to send it to 192.168.3.2, which is R2's IP address, or send it out the serial 000 interface. Big note here, whoever made this video didn't match up the topology to the exit interfaces. There is no serial 000 in this topology. It's serial 010, but you get the idea that this was meant to be serial 000. So it sends it out the serial interface to R3 after re-encapsulating it again. R3 gets it and has to do the same thing. De-encapsulate the packet, find out where it's going, do a router lookup in the routing table, and then send it on its way. So R3 does this, finds out the destination is 4.10, does a lookup, it's directly connected, send it out the fast Ethernet 00. Again, whoever was making this video said fast Ethernet, but it doesn't have a fast Ethernet. It has a gig Ethernet, but you get the idea. Send it out this Ethernet interface, which eventually gets it to PC2. It used to be that the router would use its CPU to figure out where a packet needed to go for every packet that came into its interface. In this example, there are 5 packets coming into this router. They're all going to the same destination, but the router didn't know that, so it sent it to the CPU to kind of figure it out and wasted a lot of precious resources finding out where this destination is. Once it finds out the destination, it goes out the egress interface. So traffic comes in the ingress interface, also called the incoming interface or inbound interface, processes those packets to figure out where they got to go, and then sends it out the egress interface or the outbound interface. And so you can see that that takes up a lot of processing power. This whole process was called process switching. A new method came out later called fast switching. They're all going to the same destination, right? All 5 of these packets. This time, only the first packet needed to actually bother the CPU. The rest are cached, or the answer is cached, which means we already figured out that answer, right? So we just need to forward it along. We do a quick lookup and forward it along to the egress. So only the first one actually goes up and gets computed by the processor and then gets sent out the egress. The rest of them just go through a cache, and they're going to the same destination because we already figured that out with the first packet. Cisco still thought this was too slow, and it is. So they came up with Cisco Express Forwarding, or CEF, which is the current standard on a Cisco router. With CEF, the router has already figured out all the possible destinations ahead of time and added them to the routing table. So in this situation, it's just a lookup. You're not bothering the CPU at all. This is what we've been discussing. Packets come in, the router does a quick lookup and sends it on its way. There's no processing needed. And again, if you're not in that forwarding table, if you're not in that routing table, it just gets dropped. So this section of the chapter goes through a basic review of how to configure a router. And hopefully by now you know how to do this, but it doesn't hurt to look through this section and go through some of the basic commands once again. They go through how to, well, they show you at least some examples on how to set up a host name. They enable secret, setting up a line con, setting up the VTY, doing the banner message of the day, setting up IP version 6, setting up your interfaces with IPv6 or IP version 4, and then how to save it, right? There's a ton of verification commands to make sure that what you've done is working. My favorite, my bread and butter, is show IP interface brief. This tells me all the IP addresses I have on the router, and it tells me if it's up or down. So our gig here, 000 and 001, they both have an IP address and they're both up, and that's good news. Serial 010 doesn't have an IP address, and it's administratively shut down, which means it's shut down. Nobody turned this interface on. Nobody configured this interface. We don't even need it really, but this output shows me that. You can also do this for show IPv6 interface brief if you want to see it just for IP version 6. There's the show run command, which allows you to see the entire running config. Alternatively, you can type in show running config and then the interface that you specifically want to see, and it would just show you that. More on another alternative method to do this later. You could do show interfaces, where it will show you a lot of information about specific interfaces. So in this case, they did show interfaces gig 000, and it shows you all the specific information about that interface. Show IP interface shows you more information about IP on that, the protocol IP on that interface, which we can do with IP version 6 for both of those. Show IP route shows me my routing table. Show IPv6 shows me my IP version 6 routing table. And then there's ping, which will verify whether or not I'm able to actually reach another network. There are options that you can do to filter out your verification commands, the responses to that. So for instance, they have the section, include, exclude, and begin. So as an example, they do the show run command, but they did a section. So you would do a pipe here, and then you type section and then whatever you want. So like for instance, line VTY, and it would just show you the line VTY section. You can also do the pipe and the include command and just say up. So for instance, if you did this on show IPv6 interface brief or show IP interface brief, it would only show you the interfaces that are actually up. On this one, they just decided we're going to exclude the unassigned interfaces. So anything that doesn't have an IP address, don't show me it. So this one's using exclude. And another one you can do is a pipe and then use the word begin, and then you can put in any command you want and it will start the output at the first instance of this keyword. So this line is almost, you know, if you don't have a default route, it'll actually say default of last resort is not set. But because this keyword is there, it'll start the output here, which means it's really just cutting off the codes and the show IP route output, which you'll see later. So when you look at a routing table, every network listed has a route source. Those route sources are either directly connected networks, they're static routes, or they're coming from a dynamic routing protocol. And so you can see here on R1, R1 needs to know about the 10.0.1.0 network, the 10.3.0 network, and the 10.0.2 network because they're directly connected. It also needs to learn about the 4.0 and the 5.0 from R2. And so you can see we know about 1.0 because we're directly connected. That's what the C means. This is what this is right here, this column. This is the route source code. And you would look up C up here and you would see it means connected or directly connected. S stands for static, and then there's a bunch of other ones in here, like for instance, O, which stands for OSPF, which is a dynamic routing protocol. So we know about 1.0, 2.0, and 3.0 because R1 is directly connected to those networks. The L source code here stands for local. That's the router's IP address on that network. So for instance, 10.0.1.1 is the IP address of the router on the 10.0.1.0 network. So you can see we know 1, we know 2, we know 3, and we're learning 4 and 5 via a dynamic routing protocol. R2 is going to have a similar routing table, but everything's going to be different because it's a different perspective. So you can see we learned about 1 and 2, which are off of R1. We learned those dynamically via the dynamic routing protocol OSPF, but we're directly connected to 3, 4, and 5, as well as this network here that goes to the ISP, a 209 public IP address. So you can see this shows up down here as well. It also has a static route. This is a default route right here that just says if it doesn't match any of these, this is the gateway of last resort. Send it to 209.165.200.226 or send it to the ISP. The routing table principles that Cisco kind of points out here is that every router makes routing decisions on its own using the information in its routing table. So every stop along the way here, each router is going to try to do a lookup and figure out what it's going to do with that packet. Which means because of their differing perspectives, they're all going to have different routing tables. And one other issue here that comes up with them having independent routing tables is that just because it's set up on R1 correctly, it doesn't mean, well, the routing table doesn't have the information from R2 to say that that information, that traffic is going to come back. What I mean here is that when PC1 tries to ping PC3, it sends off its traffic to R1. R1 does a lookup and it finds out, oh yeah, it's over here off of R2. So it sends it on to R2 and it finally gets to PC3. But let's say it's something like a ping or you're expecting return traffic, right? So now it's going to come back, but there's no evidence on R1 that R2 is even aware of PC1's network. So it could die right there. So that's what they're saying is that R1 has no idea whether or not the traffic can get back to it. So you can see an example of our routing table entries. Number one here is the route source. So this one is OSPF. Again, we would be able to look at those codes to figure out what that is. You get used to certain ones, C's, S, O, um, D is another big one. We have our destinations. So in this case, 10.04.0/24. Number three here is the administrative distance. Cisco calls this the trustworthiness of the route source. We're going to talk about this over in 14.4.12, but essentially what it is imagine for a moment you had multiple routes to the same destination. It really has nothing to do so much with trustworthiness as what's the preference. If you have multiple routes in your routing table to the same destination, which one would you use? Would you use, for instance, would you use an OSPF network route? Or would you use a static route? Or would you use a directly connected route? If you had network entries for a directly connected, a static route, and an OSPF route all to the same destination, which would you want to use? Well, the directly connected one makes the most sense because it is directly connected, right? I don't want to send it through another router. So we would choose the directly connected. Point is, the administrative distance tells the router to prefer one route entry over another. Now, you're not likely to ever see a directly connected and a static route and a dynamic route at the same time, but it could feasibly come up, which is why it exists. More on this again later. Number four here is your metric. The metric is just how much or how far away is the destination network. And this metric changes based on which dynamic routing protocol or which, what we're actually using. So for instance, and we'll talk about this coming up, OSPF gets there based on something called cost. It figures this out. Cost is essentially bandwidth. So it makes its decision all based on bandwidth, whereas a different routing protocol may make its decision based on hop count. Hop count may just say, this is how many hops it would take to get to that destination. More on that later. Number five here is the next hop. So this is the, up here in this example, it would be R2's IP address, where we're sending it. We have a timestamp for how long we've known about this route, and then we have an exit interface, in this case, serial 011. And the IPv6 routing table looks exactly the same. The difference is it doesn't have a timestamp. Otherwise, we still have the route source, the destination, an administrative distance, a metric, a next hop, which they use link local addresses for, and then an exit interface. So we already talked about directly connected networks. These are in your routing table because your router is directly connected to them. Static routes are statically set by the network administrator. And here they're telling you the best reasons to use a static route is if you have a stub network or a stub router. A stub router just means that we have this network over here where there's nowhere to go with it. So that would be a good usage of a static route. Another reason why you'd want to use a static route is for a very simple network. If you have a very complex or big network, you're going to want to use a dynamic routing protocol. To configure a static route, we're going to do that in module 15, but it's not hard. You go into global config and you type in IP route and then whatever our destination network is. So in this case, 10.04.0, the subnet mask. So 255.255.255.0 for a /24. And then the next hop IP address or R2's IP address, essentially send it to 10.03.2. And that's all it is. That goes into the routing table, as you can see here. And now, whenever a packet comes into R1 looking for 10.04.0, it's going to send it off to R2, where R2 will then figure out where it needs to go. The same is done for IP version 6. The command is just now IPv6 route. the destination address plus a prefix, and then the next hop IP address, which can either be the IP address of the interface, or you can use the link local of R2. Um, Dynamic routing protocols are great because, I mean, they're dynamic, right? If an interface, again, on R2 goes down, R2 is going to update R1. And R1 may try at that point to route around the issue. Maybe there's an R3 over here and R3 is connected to this network or has a different path to that network. You can think of bigger networks than this where a dynamic routing protocol would come in would come in handy. Um, Static routes, again, would only be used, you would only really want to use it in a small network, or if you have something specific that you just wanted to add to the router. Um, you wouldn't want to do in a huge network with static routes. Dynamic routing is what you want because it changes based on the conditions or just the actual topology of the network. Dynamic routes show up in the routing table just like a directly connected or a static route. As you can see here, they come with timestamps, next hops, and exit interfaces by default. So this is the IPv4 output, and you can see the IPv6 output. Still, the thing is still the same though, where we're still looking for these destinations. This is how to get to them. And again, the last one here is the default route. The default route is, again, that catch-all. It's the last thing that it's going to use, any router would use. But essentially, R1 doesn't have a route to Google. So, we would use the default route, push it over to R2. R2 would then use a default route, push it over to ISP. And so you can see on R2, we have a default route that says go to 209.165.200.226, and it would send it to the ISP, and the ISP would route it better than R2 could anyway, to get to where we're going, Google or whatever. You can see the structure of the IPv4 routing table. If it's directly connected, you can see we have multiple entries related to this. So we have a directly connected, plus we have the local, so our IP address on this network. So it indents it. So you see the 192.168.1.0. Here's that network, and then here is our IP address on that network. You don't get that for a remote network though, because there's only one. So these aren't indented. This, for a 192 on a small network, this doesn't really show you much. But when you see like a big 10.000/8 network, you can see how it indents everything. So here's a 1, here's the 2, the 3, the 4, and the 5. On IP version 6, they don't indent anything. It's just here they all are, just in order, and there you go. The administrative distance, again, if you have multiple routes to the same destination, which path or which entry would you use? And so Cisco came up with this table, and this is why I kind of shy away from saying it represents the trustworthiness of the route, because it's the trustworthiness as Cisco sees it, and Cisco puts their bias all over this. And there's a lot of logic here, first off. So, I mean, don't let me, kind of be jaded about this. But you can see like the directly connected is actually at the top of this chart. So the lowest administrative distance is the more trustworthiness of that entry. So you can see it's 0 for directly connected. This is the best possible route. Why? Because we're directly connected to it. A static route gets the next one. And the reason is because you as a network administrator are manually adding that route. So therefore they assume you know what you're doing. So that's why it's next on the list. After that, you can see EIGRP gets in here. EIGRP is Cisco's dynamic routing protocol. A lot of people would tell you that OSPF is a better routing protocol, but OSPF is not Cisco's routing protocol. This is what I meant by Cisco and their definition of trustworthiness, right? but it's not very often you would have, two routes, one learned via EIGRP and another learned via OSPF. It's just that, that they still created the chart. They're going to put their routing protocols above anybody else. So this last section has to do with whether or not you would use a static route or a dynamic route, and the differences between the two. And so this table is really good because it does a comparison on these features for dynamic routing and static routing. So for complexity, dynamic routing doesn't care. It works great in a small network, or it works great in a big network. The only downside to dynamic routing really is that it's going to use up a lot of CPU and memory and bandwidth, because it has to talk to R2, for instance. It has to figure out new routes as they come in. It has to do a bunch of crunching, uh, processing to essentially figure out what are the best possible routes and put those into the routing table. Static routing doesn't do any of that. You set it and you kind of forget it and walk away. That's it. So it doesn't do anything if there's a topology change. A topology change means, what if somebody comes in and they cut a cable, right? Well, static routing, we're we're going to have to go in there and intervene. Whereas dynamic routing, they'll adapt to the topology, and we're at least okay. If we have redundancy going on, we're definitely okay. With static routing, you're kind of hosed. Scalability, dynamic routing is the best for that. Um, Static routing doesn't really scale. I mean, you can, but you'd have to set it all up ahead of time. It's really meant for simple topologies, whereas dynamic routing is really meant for complex networks, but it's good for simple as well. Security, dynamic routing, you can set up security, but um, static routing will be more secure because you as a network administrator are statically setting um, the routes. The only time static routing would actually, or for security, would become an issue is if somebody broke into the router, hacked into the router, and started messing with all of your routes. So security is inherent for static routing, whereas with dynamic routing, you have to configure it. They talk about the evolution of dynamic routing, and you can go through all of this if you want, but the ones that are the most important now anyway are the ones mentioned in this table down here. So we have interior gateway routing protocols and we have exterior gateway routing protocols. An interior gateway routing protocol is what we've been talking about, really. It's what you would use on your own network. An exterior gateway protocol would be something that you would use between those networks. So ISPs or big networks would use an exterior gateway routing protocol. There's only one under this. It's called a path vector, and that protocol specifically is BGP. There's a couple variants of it, but it's all just BGP. On the interior gateway protocol side, we have two types. We have distance vector and we have link state. Again, not totally necessary for you guys to understand this. We're going to get into all of this in CMCIS 153, but you guys should at least be aware of these protocols, at least have heard of them. So for IP version 4, we have RIP version 2. There's also RIP version 1. RIP version 1 was class full. RIP version 2 is classless. And then RIP-NG, which came out in 1997, is for IP version 6. We also have EIGRP and EIGRP for IP version 6. Both of those fall under the distance vector. Under link state, we have OSPF and we have something called ISIS. ISIS stands for intermediate system to intermediate system. Essentially, it's a fancy way of saying router to router. But there's two versions of each of these. Version 2 of OSPF just really means it's running IP version 4, and version 3 means it's running IP version 6. So every routing protocol is going to be different. They're going to make up their decisions based on a variety of things, but like metric and so on and so forth. They all run different algorithms, and they all have to keep each other updated. So the first thing a router will do is it'll send out updates to R2 and R3 here and just say, these are all the networks I know. And then R2 will send out what it knows, and R3 will send out what it knows. At this point, they're considered converged, which is to say they're all on the same page. Everybody knows what everybody else knows or is supposed to know, right? So now if, if a PC that is hanging off of R1 wants to get to a PC hanging off of R3, R1's going to make a decision. Do I send it straight to R3 or do I go to R2? Figuring out the best path, that's kind of the whole point of routing anyway. But down here, they go through and they tell you about RIP, OSPF, and EIGRP. The short version is that RIP will make its decision based on something called hop count. And so we can see here we have options. I can either send it through R2 to get to R3, or I can go from R1 to R3. But you can see the bandwidth between R1 and R3 is only 100 meg, whereas between R1 and R2 and R2 and R3, it's 1 gig. So the fastest route is actually from R1 to R2 to R3. In fact, it's way faster, right? But RIP doesn't care. RIP does its metric based on hop count. So RIP will take the shortest path, which is not the best idea. A routing protocol like OSPF or EIGRP that bases its decisions on bandwidth, they're going to decide to go this better route here, the faster route, right? So it'll go that way. The last thing here is about load balancing. What if you have multiple routes to the same destination and they don't, they're all the same? R1 to get to PC2 could send something to R4 or R2. It doesn't matter. He can't go wrong really. But we have this thing called load balancing, which means that when the PC sends off all of its packets, right, there's going to be multiple packets. Nobody sends just one packet of anything. When R1 gets it, it's going to send some of that traffic to R4 and it's going to send some of that traffic to R2 because we don't want to overwhelm any of these links. So you can see it just load balances it across there so that no one device is overwhelmed. That said, if R4 goes down, dynamic routing kicks in, they all tell each other, and then everything goes through R2 and we're okay. So that's load balancing, and that is module 14.